I would like to ask you a quick question about your availabilities on Friday. Do you have lessons on Friday?
No.
No.
Fridays I don't. There's no.
Okay. Because I checked the timetable, but sometimes there might have been something which might have been scheduled by other lecturers, and haven't actually been listed. That's why I'm asking. Now, the reason why I'm asking is because I'd like to try to finish off this unit, this topic here today, so that we can then move on to information security. All right. But in order to be able to cover all of the material that you'll obviously need for your exam, I would need some extra time. So what I'm proposing is that on Friday, all right, we'll schedule an extra session from 6 till 8 online, like we're doing here. But obviously, instead of meeting in this room, we'll meet in the other room. And I was wondering whether or not that would be okay with you.
I'm referring for the 19th, this same week.
If we can do it this week, yes, that would be ideal, because that will give us more time if we need to schedule extra sessions in order to do so.
Personally, I can do the meeting. I don't know the others.
From my end, it's okay, as long as we have the dates in advance.
No, what I'm saying is that we'll start off for this Friday. All right, try to get as much done as possible, so that we'll have Friday and next Monday, and then we'll have the following Monday as well. Because then obviously we'll be in a situation where there isn't much time left before the exam proper. No.
Gavin won't be able to join us. Right, for work. I don't know if Alex, if I'm not mistaken, Alex works in shifts as well. I don't know.
Yeah, I have evening shifts as well, and I know for some Fridays, introduction to information system asked us to do some Fridays as well.
Do you have any other dates where you don't have lessons?
Sorry if I may. I think you're discussing further lessons.
We're discussing the possibility of having extra sessions, so that we'll be able to cover the material of Introduction to Information Security together.
How many extras we want?
For the time being, I'm asking for one.
Okay.
But I'm not excluding the possibility of having an extra one scheduled on another Friday later on.
So that means it would be two.
Exactly. We have this week, next week, and the week after that, which basically encompasses this academic year.
Okay. In fact, I think the information asked us for another day as well already, and I'm not sure whether it's going to be this Friday. I'm not sure whether Mr. Joe, what's his name, Joe Vella, asked us for an extra lesson, and we asked, we pulled. He sent us an email. It could be a Friday or so, but I did not receive any response. I'm not sure if my colleagues received anything.
Nothing from my end as well.
Okay.
I don't know if instead of Fridays, so ovviamente I don't know the timetable of my colleagues as well, and even if I wanted to work. Maybe instead of a Friday, maybe we can shift it to another day in the week, potentially Thursday or Wednesday.
As Gavin has been mentioning in the text, is that he has lessons every fortnightly for information systems. Would that mean that you would have this Wednesday? As in this Wednesday. If I say this Wednesday, does anybody have another lesson? Because if somebody else has another lesson, then it's going to be a bit pointless.
Wednesday I don't have, but I'm not sure the others.
I will have access and basically security on this Wednesday.
This Wednesday you have
Yes.
security. All right.
This is an explanation, at least.
No, I think it's scheduled fortnightly rather than every week
Yes, exactly. Schedule fortnightly.
because Gavin has the same issue.
Yeah, exactly.
All right, and the following Wednesday you wouldn't have. Does that am I understanding that correctly?
Yes, exactly. But I need to double check with the work shifts as well. That well, yeah. Let's see.
All right. Mara, let me be clear. All right. When it comes to the information systems material, all right, if you actually follow the slides, you can actually gather all of the material that we have. All right, so that is doable. All right, as in what I wanted to do is to actually have the ability to actually go through it with you in class. Another alternative, all right, would be meeting up earlier and finishing maybe a bit later on a Monday. So say starting at 5:30 rather than 6, for example. You know,
Yes, but 30 minutes will cover the extra 1 or 2 lessons.
we'll be able to take a little bit for the rest of the lessons. I'm saying maybe half an hour before and maybe quarter of an hour later. You know.
Every time, you mean?
Yes.
Okay.
Yes. That's another alternative.
Can I suggest something? Maybe you can drop us an email, and maybe until Wednesday everybody gives you the suggestions. I'm not sure. The 3 days, let's say.
And the thing is that we will need to have an answer
This week. Okay.
very quickly. So if needs be, you know, to go. It's
Yes,
only
I understood that. Okay.
I don't know for the others, but for example, for me it will work to finish on Monday, maybe 30, 45 minutes later. I mean, I know it's a big stress after day at work, but I don't know how the others will feel like it about it.
I know it might be a bit stressful, but you know, I'm trying to give you more. You know, at the end of the day, it was a larger class as well. You know, to go online also has its own issues. So,
May I ask, obviously, if possible, educating, because earlier might be a little. I don't think that I would be able to join earlier because of work.
right.
Third class, I don't know. Obviously, I don't know the rest of the others. It would be okay if we start for it until at 6, but finish a little bit later.
Say from 6 till 9. You mean? Probably everyone would be a bit tired, but yeah, I would be able to do that if needs be. But that's me.
For me, it's good too.
Maybe we can have a 5-minute break.
Yes, I will give you a 5-minute break in order to get a coffee. No
Or
problem.
10 minutes.
Or it's a 5-10 minute break to get a coffee, and then we'll continue. Yes, we can do that.
And if anyone is doesn't have the possibility to join for that hour, I'll be available on Mondays, and I'll be recording those lessons like I've been doing for the last lesson, so I'll be able to share them if
Excuse
needed.
me. I'm sorry. I didn't understand you.
I'll be available on Monday after 8, so I'll be recording the lesson like I've been doing with the previous ones, so I'll be able to share those if somebody's unavailable
Okay. All right.
to attend after 8.
We'll try to go from 6 till 8:45. All right. So let's not go all the way up to 9. I understand it might be a bit hectic, but I will give you a break in between as well. All right. So for the time being, we'll keep to that. All right.
Okay.
All right.
Agreed.
Agreed.
Okay. Mara, last week we were talking about signed notation. We were talking about the two's complement. We also talked about the signed access notation. We also talked about how to do addition, multiplication, subtraction, and division in binary. Today we're going to focus a little bit on access notation as well as fractions. All right. We mentioned the idea of access notation last time, where access notation essentially works by introducing an element of bias. Okay. Essentially, what we do is we keep the normal progression of numbers and treat them as though they are integers. However, whenever we are working with those particular binary numbers, we always need to keep in mind that those numbers, all right, the values of that or the apparent value of those binary numbers are not the true values. You'd actually need to subtract the bias that is added to it. So essentially, if we have an 8-bit, all right, if we have an 8-bit access notation, all right, the bias will generally be 2 to the power of n minus 1, where n, okay, is this n, all right, that is basically your number of bits that you're using within your representation. So essentially what we're talking about here is 2 to the power of 7. In this case, that will give us a value of 1 to 8. All right? So essentially, what we would do, all right, in order to represent the smallest number, right? If we are using 8-bit, then we would need to represent it in this way, all right? We'll have 8 bits, so 8 zeros would be the smallest number that we can represent, all right? And that goes all the way up to 8 ones, all right? Like so. All right, and it will grow normally. Okay. However, this over here, even though we're normally associating that with 0, all right, as a value, that will need to take into consideration the bias we talked about. So therefore, we'll need to negate 1 to 8 from this. All right. Therefore, this gives us the true value of minus 1 to 8. All right, here. All right. On the other hand, on the other extreme, okay, 8 ones will actually give us the value of 255. If you work it out, it will actually come up to 255. All right, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 1 to 8 is 255. Negate 1 to 8 from that. That would give us the true value of 1 to 7. All right. The cool thing about this is that essentially when it comes to seeing the progression within binary, that also represents the progression within the value of the numbers. You can automatically say that this is smaller than this, and this is they're just smaller than something like that, all right, and so on and so forth. Okay, 0 in this case would look something like this. It would be 1 followed by all the zeros, all right. That will actually be 128 minus 128. Therefore, it will have the true value of 0. All right, so notice that these numbers, which I'm underlining, those are actually the true values. These ones over here are the apparent values, and then we need to take into consideration the bias in order to get the true value. All right, that is basically what we talked about in terms of the excess notation up to this point. Now you might be asking yourselves, what is the whole point behind this? The whole point behind this is because this particular notation, all right, is particularly useful when it comes to actually representing fractional numbers, all right, which we're going to be covering on a bit later on today. Okay. So over here we have another worked example. So if we take the value 100110001, all right, base 2, we know that this is 2 to the power of 0, this is 2 to the power of 3, this is 2 to the power of 4, and this is 2 to the power of 7. So we add them up all together. We have 1 to 8 plus 16 plus 8 plus 1, which gives us the apparent value of 153, all right? But we need to take into consideration the true value or the excess value. So we need to remove the bias, all right, this over here. All right, I know that these should be to the power of not as they are written down over here, right? So whenever you see something like this, that in the slides should be 2 to the power of 7, like so, okay? So over here, we get 153 minus 2 to the power of 7, which is 153 minus 128, which is equal to 25. All right, and that works out for every type of excess notation number that we can think of. We can actually see other worked examples over here as well. Okay. So I'm going to skip these worked examples so that you can go through them on your own time, so that I do not eat up too much time going over this. Like, essentially, the task whenever you're working with excess notation is treat it as though it is a normal unsigned binary number. All right, find out its value, then remove the bias. All right, in order to convert from binary into decimal. If you're going the other way, all right, so from decimal to binary, you would first need to add the value. All right, this is all right going from decimal, all right, minus 24, and we want to convert it into 8-bit excess notation. So what do? We take minus 24, we add the bias, all right, which gives us the value of 104, and you would convert this 104 as though you were converting an unsigned integer, and it will work out in exactly the same way. All right, so essentially, you could use the weighted method, you could use the division method. It's up to you. All right, if you use the weighted method, it's probably a bit shorter, but essentially that's what you would do. So if you have 104, all right, remember that we have different weights. We have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7, all right, thus giving us 1, 2, 4, 8, 16, 32, 64, and 1 to 8. And essentially, the way that you work it out is you go through each power, all right, and say, all right, 1 to 8, how many of that goes into 104? 0 times. 64 goes into 104, which leaves 40, so we'll have 1, all right? There, remaining 40, all right? 32 goes into 40 once, so you have 1 there, okay? That will give us a remainder of 8, all right? 16 doesn't go into 8, so you'll have a 0 here, all right? A 1 here, and the rest will be zeros, because essentially you would have crossed those out. Okay, and that is essentially how you would convert the value of -1 to 4, all right? So this would be essentially the unsigned integer notation. This would be your excess notation value, all right, with a bias of 1 to 8. Any questions up to this point?
No, thank you, sir.
Okay, and you obviously have another worked example, all right, over here with different values just to showcase how this can work. So, what are the advantages of this system? First and foremost, it can represent positive and negative numbers, just like the 2's complement. You only have one representation for 0, unlike the signed integer notation. It is easy to compare two numbers, and when comparing bits, all right, you treat them as unsigned integers, all right? Access notation, as we said, is normally used to represent integers, but is predominantly used within floating point representations that we're going to be seeing in the next set of slides, which I'm going to start here. All right, so far, all of the numbers that we've managed to represent thus far were always whole numbers, all right? However, there are by far more fractions or parts of whole numbers than there are actually whole numbers. In fact, between two whole numbers, there is actually an infinite number of fractions that one can actually represent, all right? So how can one go about this? All right. Now, first and foremost, all right, whenever we represent fractions in a decimal format, essentially we what we introduce is what is known as the decimal point. All right. So essentially, what we're doing over here, if we a value, so I don't know, Bridget, give me a decimal number with 3 significant figures, if you will. So essentially, we have 0.842, all right? We call this value over here as our units, if you remember. However, this first place behind the decimal point, that is basically our tenths, all right? This here would be our hundredths, all right? And this will be our thousands, all right? In the sense that this particular value here, all right, that is equivalent to 2 all over 1000, whereas this value here, that is equal to 4 over 1000. Or sorry, 4 over 100. And this here is 8 all over 10. Essentially, adding those together will give us this 8.842. Does everybody agree with me with regards to this?
Yes.
All right. So, in a very similar fashion, all right, when we talk about binary, okay, so if we have the following value. All right, that for us is equal to 1. Since we're working with binary, all right, so we always need to work in relation to powers of 2. So this would be 2 to the power of 0, essentially, this unit over here. This is 2 to the power of 0. If I had to move this 1 that way, essentially dividing, all right, this position over here will become 2 to the power of minus 1. All right, the next one will be 2 to the power of minus 2, and so on and so forth. So as you can see, it's very, very, very similar, all right, as a notion, all right, to what we were doing before, or if we were going in this direction, all right, towards the most significant bit, all right, the powers were increasing by 1 for each bit, all right. Going to the other side, all right, they are decreasing by 1, all right. If you're moving towards the least significant bit, you're always decreasing the powers by 1, the powers of 2 by 1 for each bit that you come across. When you cross the point, all right, notice I'm not going to call it the decimal point for the simple reason that we're not always going to be working with decimal, all right. Once you cross the point, essentially, once you cross that threshold, the powers start become negative, all right. That's essentially the difference, okay. But 2 to the power of minus 1 in reality is equal to 1 all over 2 to the power of 1. Similarly, 2 to the power of n, all right, being any n, is equal to 1 all over 2 to the power of n. Okay? So essentially moving the bit behind the point, all right, for the first bit, that is essentially saying how many halves do I have, all right? If I move it one step further, it's how many quarters do I have. If I move it another step further, it's how many eighths I have, and so on and so forth, okay? Now, you could, technically speaking, try to represent binary numbers using this method, all right? Remember when we were using weights in order to represent a number? So let's say we have the following number. So 1011 point, all right? 10011. Essentially, all right, so that I can use the same notion over here. We know that this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. Over here, we know that these are 2 to the power of minus 1, 2 to the power of minus 2, 2 to the power of minus 3, 2 to the power of minus 4, and 2 to the power of minus 5. All right? Essentially, what you can do is you can add up these powers, all right, and you will actually get the number here that you're trying to represent. Okay? In this case, we'll have 1 plus 2, all right, plus 8, all right? So essentially we have 8, 10, 11. So this is 11 base 10, obviously, point, and then you'll have 2 to the power of minus 1, all right, plus 2 to the power of minus 4, and 2 to the power of minus 5. And if you add these together, you will actually get this value over here. So the final value would be 11.059375. All right, base 10. So that's basically how you can convert from one to the other. All right. So that's one way that you can actually convert. Another way that you can actually convert is saying, let me look at this part of the number on its own. Okay, this number on its own. All right. So let me draw it out over here for you in blue. Okay. So 0.10011 base 2. That is equivalent to 10011 base 2 divided by, all right, we have how many digits here? We have 1, 2, 3, 4, 5. So 1 followed by 5 zeros. So 1, 2, 3, 4, 5 base 2. What you will do is you will convert this normally, and then perform the division. All right, and you should get the same value. All right, now let's assume that we didn't have the part in the beginning. All right, so essentially we'll convert this normally. So we'll have, so this is 2 to the power of 1, 2 to the power of 2, 3, 4, and 2 to the power of 5. Okay, so we'll have 1 plus 2 plus 32. If I'm not mistaken, 2 to the power of 5 is 32. Let me just double check. 2 to the power of 32. 2 to the power of 5. Yeah, 32. 32 plus 3. Okay, that will give us 35. This over here will be 2 to the power of 7. So therefore, we're talking about 35 division by 2 to the power of 7. 2 to the power of 7 is 1 to 8. Okay, so if you take this and divide it by 1 to 8, $64.
Sorry.
I think I did a mistake. So it's 1, 2, 3, 4, 5, 6. Sorry, it's 2 to the power of 6. I'm sorry. So 2 to the power of 6 is 64, so 35 divided by 64. Okay? So we'll have 64 here. So essentially this will then become equal to 0.546875. All right, base 10.
Can I ask you something, please?
Yes.
With regards to 10011 to the power of
This
2.
one?
Why did you start 2 to the power of 1 and not 2 to the power of 0? Maybe I'm not understanding something.
Sorry, this should, no, I made a mistake as well over there.
Okay, sorry.
So, it should be 2 to the power of 0. You're right.
I thought I'm missing something.
No. I made a mistake. Let me rewrite it. So you start off 2 away. So you'd start off 2 to the power of 0, 2 to the power of 1. 2, 3, 2 to the power of 4.
2 to the power of...
No. So 0, 1, 2, 3, 4, 5. So this is 2 to the power of 5. So essentially we'll have, so it ended up being the same answer, but it's because I did a mistake essentially. So essentially we have the value of 19, all right? Base 10 divided by 2 to the power of 5. So 0, 1, 2, 3, 4 result. 5, 2 to the power of 5, which is 32. Well spotted. Thank you for correcting me. I'm sorry for making the mistake.
No. I think I want to make sure I follow everything.
No. It's
you know?
I made the mistake myself. So I'm really sorry about that. All right. So essentially, we have 5, 9, 3, 7, 5. As you can see, all right. In fact, before my answer wasn't actually matching up. This binary number, this decimal number, or the number behind the decimal point here and the number behind the decimal point here, are exactly the same using these two different methods. Yes, Bridget, what would you like to ask?
I don't know if this is a silly question, but when we were doing negative numbers, since the computer only knows ones and zeros, we had to mess about with that. How does the computer know that it's a dot, that it's,
That is what we're going to get to. All right, that's what we're going to get to. All right, what I'm trying to work out at the moment is how would you be able to convert a number or binary number with a dot, a visual dot, back into decimal and vice versa. Essentially, that's what we're trying to do for the time being. Kind of like how we were doing that earlier. All right, but that's a very good question. Yes, when it comes to actual fractional numbers, all right, you can either specify the number of integer digits you have or integer bits you have and the number of fractional bits you have, all right, which has its own pros and cons, which we're going to be seeing, or else you use the floating point notation, which I'll be covering on later on today. Okay?
Okay, thank you.
So, are there any questions with regards to this method? I'm sorry again for making that mistake. My fault, all right? Brain fart. Happens to the best of us. Are you trying to say something, Floyd?
No, sorry.
All right. Okay. So essentially, what we've seen is two different ways of actually getting the same value. All right. In our for our fractional number. Now, how would you go about converting a given fractional number, all right, in decimal to binary? Okay. Remember that whenever we were given an integer number, all right, one of the ways that we used to go about it was via the division method. All right. With the decimal number, all right. So if we have a decimal number, I don't know. Somebody give me a decimal number with a point. All right, so 0 point something.
0.932.
So 0.932. Let's start with that. So 0.932. Okay. Essentially, the methodology that you would use is you would multiply this by 2. Okay. So 0.932, and you multiply that with 2. Now that is going to give me, 0.932 multiplied by 2. All right. This is going to give me the value of 1.864. All right. What I am really interested in is this part. All right. So I'll take 0.864 here and multiply it by 2 again. So I'll take 0.864 multiplied by 2, and that will give me 1.728. Again, take this number here, okay, and I'll write it over here. So 0.728 and multiply it by 2 again. So 0.728 multiplied by 2. So I'll have 1.456. Again, take the 456, 0.456. I'm trying to see whether or not this is actually doable with an 8-bit stump. So 0.456 multiplied by 2 will give me 0.912. Again, 0.912 multiplied by 2 again will give me 1.824, and you keep on going on and on and on until this number here, or rather, the answer that you get on this side, all right, would become an integer, all right, i.e. a whole number, okay? Essentially what you would do is you would read the values. That would be your most significant bit, and you move downwards. So essentially 0.932 is going to be approximately equal to, all right, 0.11101, etc. All right, obviously for the rest of the number of points that you have over here. Okay, so this number, as I said, this is your most significant bit after the point. All right, and the further down you go, obviously it becomes lesser and lesser significant. However, as you can see over here, it might not necessarily always be the case that the number that you're going to be able to extract is going to be exact, is going to fit within a certain number of bits. Okay? If we take, for example, this number over here, right, 0.6875 multiplied by 2 would be 1.375. You take the 0.375, multiply that by 2 will give us 0.75. 0.75 multiplied by 2 will give us 1.5. Take the 0.5, multiply that by 2 will give us 1. So this would be the exact representation of 0.6875 base 10 would be equal to 0.1011 base 2. All right. However, there are situations, all right, which I suspect this could be one of, all right. Obviously, I would have to continue working it out, whereby there is a non-terminating binary fraction. So if we take, for example, the simple binary number of 0.2, right? If you multiply that by 2, will give us 0.4. 0.4 multiplied that by 2 will give us 0.8. 0.8 multiplied by 2 will give us 1.06. 0.6 will give us 1.02. All right, and then again, essentially, you're going to start back where you started off from. So this is going to never end. So essentially, 0.2 base 10. Essentially, if you had to represent it in 6 bits, all right, it will be 0.001100. If you're using 8 bits, you will include another 2 ones. If it's 10 bits, all right, you represent, and it keeps on going in that same pattern, all right, forever, all right. So essentially, you're going to have some form of error introduced depending on the number of bits you're actually using in order to represent that fraction, essentially. Okay? So whenever we're talking about a fraction, all right, a number which is fraction, the magnitudes that you can actually represent is also going to depend, or the magnitude of the error, rather, that you're going to have is going to depend entirely on the precision that you have. Okay? Now, obviously, the more bits you use in order to represent a fraction, all right, the more precision you have. Okay? So, how do we calculate error and how do we calculate precision? Because that's an important aspect. So, let's say that we take that 0.2 example, all right, and we're trying to represent it in 6 bits. In 6 bits, 0.2 would look like this, all right? If we then convert it back into a binary, into a decimal, sorry, okay? No, the error is not due to numerical overflow. It's actually the opposite. It's numerical underflow. All right. We'll get to that, okay, in a moment. So essentially, what we're doing over here is we're converting this 6-bit, this fraction into its decimal format by taking this number, considering it as being an integer, and then dividing it by the number of bits that we're actually representing. All right, 1 followed by the number of bits that we're using in order to represent that number. All right, 1 followed by 6 zeros in this case. All right, this value gives us 12. This value here gives us 64. Therefore, the value that we are actually representing with 6 bits is 0.1875, which is not exactly 2. All right, as you can see, there is an element of error. Therefore, the absolute error is, all right, 0.2 base 10 minus 0.1875 base 10, and that would give us 0.0125 base 10. That is basically your absolute error. All right, why is it called the absolute error? That is basically how far away you are from the actual number that he wants to represent. Then he wants to understand how far it is in terms of percentage away from the actual number. How do you do that? You take this number and divide it by the actual number that he wants to represent. So in this case, you take 0.0125 divided by 0.2, and you will get this value, so 0.0625, which basically equates, all right, to 6.25% worth of error. Okay? If we want to improve the accuracy over here, we would need to increase the number of bits. All right? So essentially, the accuracy with which we're actually going to represent a number is determined always by the smallest magnitude that we can represent. All right? So if we're using 6 bits, then the smallest number that we can represent is 1 to the power of 2, 1 all over 2 to the power of 6, or 2 to the power of minus 6. So essentially, the accuracy is always going to be equal to 2 to the power of minus n, where n is the number. All right, let's call it f actually, so that we're a bit more. 2 to the power of minus f, where f is the number of fractional bits. All right, that is always going to be the case in this case. All right, so here's the same example. All right, if we had to take 8 bits, if we had to take 8 bits, the smallest number that we can actually represent is 1 all over 256. 1 over 256 is 0.00390. 625, etc. The largest number that we'll be able to represent, all right, fractionally will be 0.111111111, all right, which is 255 all over 256, which is close to 1, but not quite. 0.99609375, all right, and therefore the accuracy is equal to the smallest number, all right. What exists between this number and this number? Well, so if we talk about 1, 2, 3, 4, 5, 6, 7, what is between these two numbers? We know that mathematically, all right, so this is equal to 1 all over 256. And this over here is equal to 2 all over 256, right? And so on and so forth. But we know mathematically that between this number here and this number here, there's a wealth of other numbers as well. In this case, since we do not have any form of, we cannot actually represent any form of other numbers in between those, we can say that for this particular representation, there exists nothing else in between those consecutive numbers. All right? Essentially, for this particular representation, nothing else exists. If you want to have a more finer element of granularity of representation of your number, you would obviously need to increase the number of bits. But just like in signed integers, all right, if this for us, all right, was 1 and this was 2, all right, we couldn't actually represent 1.5 with 3 bits, for example, all right? It doesn't make, we couldn't actually represent it, all right, because our representational system does not allow for that to happen. In a very similar way, over here, we cannot actually represent even sub-fractions between those two fractions over here. Like, we cannot represent fractions between these two integers over here. Are we clear with regards to this?
Good.
So good.
Okay. Bridget asked whether or not the error was due to overflow. All right. I said it's actually something that has to do with underflow. All right. Underflow, on the other hand, is basically where the bits that you would require in order to represent the number more successfully, all right, cannot actually fit within the representation that you're taking into consideration, all right? So essentially, we're saying that underflow occurs when the magnitude, all right, of the number is smaller than the accuracy that you have for the numbering system that you're using, all right? So if, say, we have a number A, all right, which in binary format is represented by this number, where we have 0 followed by 1, 2, 3, 4, 5, 6, 7, 8 zeros, all right, and then we have 1, 0, 1, 1, 1, all right, and we're trying to represent this with 6 bits, all right, then essentially we'll have 6 zeros, which equates to 0, all right? However, if for some reason, all right, I had to take this number and multiply it by 1,000,000 base 10, all right? In reality, all right, the number would actually come up to this value over here, all right? So let me show you what I actually mean, all right? If I do this, this number here, all right? So 1, 0, 1, 1, 1, all right? 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. So that is 1 plus 2 plus 4 plus 16. So this is 16 plus 4. So 16 plus 4, that's 20, and that's 23. So this value here is 23, okay, base 10. If we had to divide this by the number of values that we have over here, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we're talking about 1 followed by 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, base 2. All right? That, if we have to actually convert it, so 1 followed by 13 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Whoops, in binary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, that gives us 8, 1, 9, 2. All right, base 10. So essentially, what we're talking about here as a as a value, all right, is 23 divided by 8,192, which gives us this very small number. So this is essentially equal to 0.0028076171875 base 10. If I then had to follow that up by a multiplication with a million, all right, the number will be quite significant. It will actually be 2,807.6, etc. All right. But if we had to represent this number, all right, that we have over here using 6 bits, we wouldn't be able to. All right, we'll only be representing 0, and 0 multiplied by anything is going to give us 0. So this is going to give us is going to maximize the error. All right. Notice that you can, to a certain extent, all right, mitigate the issues a little bit. All right. So essentially, the multiplication was done like this. All right. So we have, if we had this number like so. All right. If I had to perform the operations one after the other in this fashion, and we had to represent the number using 6 bits, then probably we're going to have a bit of an issue. However, what I could also do is take 23, multiply it by a million, all right, and then divide. All right, so I'll do that first and then divide that by 8192. The result will actually be a lot closer to the result that we have over here, especially if we do it in terms of binary. Do we get this this understanding, or do you understand this point that I was trying to make?
Yep.
Any questions?
Before, when you taught us how to do division and there was a remainder, we could just say remainder. Do we have to keep going now?
No,
You know what I mean?
no. In this case, if I tell you, how are you going to represent this in terms of an 8-bit fractional number, then you will keep on doing multiplications. In this case, for 8 times, essentially.
All right.
All right, so you'd stop there, but probably then the question would evolve slightly, and you'd be asked, all right, what is the error then? All right, and then you would have to calculate the error.
I see. Okay.
Okay, we'll actually see an example of an example question here in the slides. All right, so so essentially, if we are trying to convert from binary to decimal, and you know where you have your fixed point for your fraction, for your decimal part and your binary part. Essentially, there are 2 ways of going about it. First and foremost, if you're going from binary to decimal, what you do is you would convert the integer part on its own, and then convert the fractional part on their own, and then combine them together like we saw earlier. Or else, what you could also do, all right, is assume that the entire number is a whole integer, and then just divide by the number of bits that you're using in order to represent the fraction. Let's see an example. So let's say that we have this number, all right, 100111101, all right, and let's say that we want to represent it with 3 bits for our integer part and 5 bits for our decimal part. All right. The one way that you can go about it is literally splitting it up. All right. Notice these have to be known. Okay. So you'd say, all right, let's convert the integer bit. The integer bit is 4. All right. The decimal, the binary bit. All right, or the bit, point, but after the point, all right, the bits after the point actually equate to these two numbers, all right. So we ignore the fact that it is actually a fraction, all right. We'll treat it as a normal integer, all right, and we'll convert this as a normal integer, but then we'll have to divide by the number of bits, all right, that we're using in order to represent. So 1 followed by 5 zeros in this case. So this value comes up to 29. This value is 32. So 29 divided by 32 will give us the value of 0.90625. All right. Therefore, the whole number is 4.90625. Okay. The second method is probably it's a bit easier as well to a certain extent. Is you treat this as though it were an integer, a whole integer. That would give you a value of 157. We know that the fractional part, all right, constitutes 5 bits, which is equal to 32. Essentially, what you would do is you take that number and divide it by 32, and you'll get the same answer, essentially. All right, so either one would work. All right, over here you can also see another example. All right, using the same method. All right, so this would be an example question. You'd be given a binary number. You would be given the number of integer bits and fractional bits that you would have. All right. In this case, you're asked to do both methods. All right. This is the first method. This is the second method. Essentially, both will work as well. Personally, I prefer the second method because it tends to be a bit shorter. All right, but both methods are equally valid. Okay. This would be an example that's I was telling you about Bridget earlier. So over here we have the number 5.43, all right, and you are asked to assign it to an 8-bit number using 4 bits for your integer part and 4 bits for your fractional part, and you are also asked to calculate the error. You know that 5 is in 4 bits is represented as 0101, all right. 0.43, if you use the multiplication method, will result in this binary number. So 0110111, etc., etc., etc. We know that we have to only take the first 4. Okay, so therefore you would ignore literally the other bits in this case. All right. So the number that you can represent using 8 bits is 0101 for the integer part and 0110 for your decimal part. However, if you had to take this this number as a whole, all right, okay, so ignoring the decimal point, all right, that would give us 86 if we had to convert it as a normal integer. If we had to then divide 2 to the power of minus 4, which is to the power of 4, sorry, which is 16, all right, for the fractional part, that would give us the value that we're truly representing, all right. This number actually represents 5.375, okay, but then we can calculate the error. In this case, all right, the error is 0.055. That would be the absolute error. If you take this and divide it with the actual number that you wanted to represent, it would give you a value which is just over 1%. Okay? So the relative error will be 1% in this case. So far, so good?
I still didn't understand much how error is calculated.
Mara. So, first and foremost, do you understand how we actually managed to get to this point over here?
Yes, so till then it's okay.
All right. So essentially, the absolute error, all right? So the absolute error is basically the number you want to represent. Okay, minus the number you are representing. That is essentially what you're doing. So when we're taking the number that we want to represent, in this case, all right, we have the number 5.43. Actually, let's write it in red because 5.43. And we negate the number that we're actually representing, which is this 5.375. All right, the answer over here is going to be equal to 0.055, which is essentially your absolute error. So far, so good?
Yes.
All right. Relative error. All right, is equal to the absolute error all over the number you want to represent.
So that's how you get the percentage.
Yes.
All right.
Okay, so in this case, okay, we're taking the value of 0.055 and dividing it, right, by 5.43. Okay, we actually have to calculate it like so. 0.055 divided by 5.43, which is 0.01, etc., which is approximately equal to 1%. All right, it's slightly bigger, but it's nearly 1%.
All right, it's understood. Thank you, sir.
All right, any other questions, guys?
It simply means you're just finding out how off you are, no? So it's the
Yes,
target number.
Yes. It's in order to represent how far off you are, because
Exactly.
it's not always possible in order to represent this number. Now, obviously,
Exactly.
there are a number of other examples on the slides which I'm going to gloss over. I would recommend that you take a look at them in your own time. And if there is something that you don't understand, please do message me. All right? As well. Essentially, it's exactly the same thing over here. Okay? Issa, the problem or the balance that you're always striking whenever you have a fixed number of bits, all right, for representing your integer part as well as your fractional part, is that you're always battling between the range of numbers that you can actually represent versus the accuracy. All right, the more bits you use for the integer part, obviously, the larger the range you're actually going to be able to span. All right, whereas the more bits you have for your fractional part, the bigger your accuracy is going to be. All right, and we can actually see this via this table over here. All right, so if the number of integer bits is 0, all right, and the number of fractional bits is 8, all right, then the smallest number that you can actually represent, all right, is minus 0.5, whereas the biggest number is 0.4960937.5. All right, but the accuracy is going to be quite high in that case. On the other hand, all right, if you have 8 bits for your integer and 0 bits for your fraction, then essentially what we're saying is that your smallest number is going to be -1 to 8, and your biggest number is going to be 1 to 7. However, your accuracy is in steps or in increments of 1. Okay? So in this case, whenever you're going to decide the number of bits that you're going to use in order to represent the fractional part as well as the integer part, that is going to have a massive effect on your expressive power with regards to the numbers that you're going to try to represent. Okay? Ideally, we would have a situation whereby we could represent both a large range as well as have high accuracy. And that's where the idea of the floating point comes in. Essentially, the floating point, all right? If you think about it as a term, floating means that it can move around, all right? It floats from one position to the other, all right? And that is what the floating point representation actually allows us to do. It allows us to adjust our point, all right, where it's going to end up within the number, all right, for our value, all right, depending on whether we're trying to represent larger numbers or whether we're trying to represent smaller numbers. It will automatically adjust, all right. Now, in order to do this, all right, we will actually make use, all right, of the of some form of scaling factor, all right, which essentially is the value that we're going to be using in order to represent our number. So essentially, if I have this this binary number, all right. So I'm going to use the one in the slides just so that we're clear, all right. And we have a scaling factor of 5 or fractional part of 5. Then essentially, if I multiply this by 2 to the power of -5, essentially this number will then become 0.011.01011. All right. If this were -6, it will move. The point will move here. All right. If it were -4, then the point will move there, and so on. So essentially, this number over here is going to determine where my point is actually going to shift. Do you agree with this?
Yeah.
At least for the time being.
So if it's a minus, it shifts.
It's always going to. In this case, it's going to shift. If it's a minus, all right, then it's going to shift the point from here that way. If it's plus, then it's going to shift it that way. Okay? But essentially, this number here is going to determine by how much this point is actually going to shift. In this case, if we're going to shift by 5 points, then it's 1, 2, 3, 4, 5. Therefore, it will have to be placed over there. Correct? All right. So, essentially, what we're saying is that we have a value, all right, of by what we call an exponent. This, if you think about it, since we're doing it is the value that we're powering this number, all right? We call that our exponent, all right? This part over here, this is going to store the value itself. This we can call the significant, all right? Or value, all right? But in floating points terminology, this is known as your mantissa, all right? Don't be afraid of a new word, all right? Probably none of you have heard of the term mantissa, but essentially mantissa means value, full stop, all right? Let's keep it simple, all right? The reason why I'm introducing this term is because that it is a term that is commonly used within floating point representation. So essentially, our number is going to be our mantissa, all right, multiplied by 2 to the power of our exponent. Okay, and this is going to be able to represent all of our floating point values. So far, so good.
Yes, okay.
All right. So essentially, what we're saying here is that our binary number will somehow need to represent what? Okay, our mantissa as well as our exponent. All right. It will need to represent both. Okay. So we're saying that we need 2 parts of our binary to be dedicated to these 2 components. All right. Now, the thing that we need to keep in mind is that if we increase the number of bits for our mantissa, that is going to allow us to determine the accuracy. All right. However, usually we the mantissa, all right, or assigned mantissa, all right, is usually a value, all right, that we determine as being something like this, 0 point, etc. All right. Normally, a mantissa is represented in this number. This is so that our extreme left in this case is going to be our radix point, all right, or our binary point, if you will. Okay. The other bits that are not used for the mantissa are going to be used for our exponent. All right. Now the exponent is what is used in order to determine our range. So our mantissa is going to determine our accuracy. Our exponent is going to determine our range. All right. Now the exponent is represented using excess notation. Hence why we did excess notation before. Okay? So it will have a bias, etc., etc., etc. Probably you would also want to be able to represent positive numbers as well as negative numbers. All right? So usually what you would have is your floating point will take on a form like so. You would have 1 bit which is reserved in order to determine the sign of your value. All right. The next 3 bits, all right, which in this case for an 8-bit floating point notation, obviously, the next few bits would be in order to represent your biased exponent. All right, using notation. The rest will be used, all right, for your mantissa magnitude. All right. We're always assuming that it's going to start off with a radix point over there. All right. So essentially, we are assuming that this is 0 point something. Okay. So over here we can see that we have for an 8-bit floating point representation. All right. We have 3 bits for our exponent. All right. We know that this is using excess notation. So we know that the bias for this, all right, is unless specified otherwise, but in this case, it would make sense for a bias to be 2 to the power of 3 minus 1. So it's actually 2 to the power of 2. 2 to the power of 2 is actually equal to 4. So the bias for this exponent over here is 4. All right. So far, so good. Any questions?
Can you repeat the mantissa sign, the first one, please?
you mean?
Because
All right. This is all right. That is like remember the signed magnitude notation where we use the first bit in order to determine whether or not it's positive or negative.
yes.
Essentially, it's exactly the same thing.
Okay.
All right. So over here, if it's 0, then we're saying that it's 1. It's positive. If it's 1, then we're saying that it's negative. That's essentially it. So
Okay.
this is going to allow us to determine positive and negative numbers.
All right. Okay.
Okay.
Thanks a lot.
All right. So essentially, all right, if we had to use this worked example, we have this this binary number. All right. So 1, 1, 1, 0, 1, 0, 1, 1. All right, and we're sorting it in the 8-bit floating point representation that we just described. We already see that our Mantissa sign bit, all right, is 1. Therefore, we can say it's negative. Okay, we can take the next 3 bits, all right, 1, 1, 0, all right, and represent that in excess notation. We know that the biased value of that is 6, all right. If we remove the bias, all right, 6 minus 4, remember the bias that we just calculated being 4, therefore the true value is 2. The rest of the numbers will be actually 0.1011, all right? So essentially, our number is minus 0.1011 base 2 times 2 to the power of 2. Okay? Essentially, what we can now do is we can convert this part and this essentially get our number. All right. So we know that this can be represented as 1011 divided by 10000. All right, which will then multiply with 4. Okay. This value is 11. This value is 16. This value is 4. All right. So essentially what we have is 44, multiplying this with this, divided by 16. All right, which gives us 275. However, it is negative, therefore minus 2.75. So this number, all right, here represents minus 2.75. Questions?
Sir, I only understood till the exponent factor there. The exponent is 1106, and then I
All right, Mana. Remember when we said in excess notation, we have a bias for each number. We have the value and then the true value that we're trying to represent. We have the apparent value and the true value. Yes?
Yes.
Mana. The bias, if you remember, is always equal to 2 to the power of n minus 1. Alright? In this case, n is 3, so 2 to the power of 3 minus 1. Alright? So that's 2 to the power of 2, which is actually equal to 4. So when our apparent value, alright, is equal to 6, then our true value is equal to 6 minus our bias, which is equal to 4. Alright? Essentially. So we're saying 6 minus 4, which is equal to 2. That is our true value.
Okay, yes, I understand. So till there.
Alright. So that is basically what we did over here. Alright? Notice that we are talking about an 8-bit format. So essentially, the last 4 bits are going to be our value, our Mantissa. Is that okay?
Yes.
And we're always saying that our Mantissa starts with a 0 point and then the four bits for this 8 bit representation. So it basically comes up to this number. Since our sign bit was 1, then it's negative. So essentially we have our mantissa, that is this part here is our mantissa. Sine and all right? And this part here is our exponent, which is basically following this notation. Notice mantissa times 2 to the exponent times 2 and the exponent. So far, so good?
Yes. So what I'm not sure about is the 0.1011. I'm still not sure about it.
Do you agree that these are the 4 bits that fall under the magnitude?
Mhm.
So essentially, whenever you see these are the 4 bits, Mala, you're saying 0.10. That's it. This is assumed. This part here, in this particular representation, this is assumed. The 0 point. These are the 4 bits that we have over here, no?
Okay, I understand now. Okay.
All right? But this is assumed for this particular representation that we have over here. All right? As we're going to be seeing, ideally we wouldn't have it as a 0 point, all right, for floating point representation. We'll actually assume that it is a 1 point something, but that is something that we're going to come to in a moment. Okay? But do you understand how I actually managed to achieve this particular representation?
Yes, I did. Thanks.
All right. Are there any other questions? All right. Seems not. Okay. So here's another example. All right. So say you have this binary number using the same floating point format that we had. This sign bit is 0, so therefore it's positive. This is our exponent, all right? So this gives us an apparent value of 1, minus 4. That gives us minus 3. Essentially, this value here, that is representing minus 3. This part here is 0.0010. All right? In fact, you can actually see the working over here. The sign bit is 0, therefore the mantissa is positive. The exponent appears to be 1, but we have a bias. The bias is 4, all right? So we'll have to take 1 minus 4, giving us minus 3 as our exponent. Therefore, we have our mantissa being 0.0010 times 2 to the power of minus 3. All right. If we then convert everything, all right, we would see that over here we have 2 divided by 16, all right, because this part represents 16, multiplied by 1 divided by 8, all right? And if you multiply all of this together, you'll get 2 divided by 1 to 8, essentially, which is equivalent to 0.015625, if you had to work it out. So if we took 2 divided by 16 plus, or rather, sorry, 2 divided by 16, all right, and you multiply by 1 divided by 8, it gives us this value, all right? So essentially, this floating point representation represents this particular number over here. Any questions?
Sir,
Yes.
if the biased exponent is 3, why did we do minus 4? That's what I didn't
It's
understand.
not Mala. Again, the bias takes 2 to the power of n minus 1. N is the number of bits that we're using for the excess notation. In this case, it's 3 bits. N minus 1, 3 minus 1 is 2. So 2 to the power of 2 is 4. So that is our bias.
All right. So I skipped a bit. All right. Okay.
Okay, so we take our apparent value, which is 1, and we need to remove the bias so that we get the true value. All right, so 1 minus 4 is actually equal to minus 3. Okay?
Thank you, sir. Thank you.
So, what about the opposite? Let me do it in the other way. So, let me rewrite this over here because it might be a bit, it can be a bit misleading, all right? Because I know that there are a bit of anomalies. This happened from a conversion from PowerPoint to PDF. So, we have minus 3.95. All right, and we want to convert it to this 8.8-bit representation of floating point numbers. What we can do is we can represent the integer part, all right, which is 3 base 10, which is equal to 1 base 2. Okay, that is 3. 0.95, all right, if we use the multiply by 2 method, all right, so multiply by 2, all right, so 0.95 multiplied by 2 is 1.9 multiplied by 2 is 1.8, all right, 0.8 multiplied by 2 is 1.6, all right, 1.6, 0.6 multiplied by 2, all right, is 1.2, and 0.2 multiplied by 2 is 0.4. 0.4 multiplied by 2 is equal to 0.8. 0.8 multiplied by 2 again gives us 1.6, and we can see that the pattern is going to repeat itself. So essentially we can say that 0.95 base 10 is approximately equal to 0. Alright, notice that this is our most significant bit, and we're going to read downwards. Alright, 1, 1, 1, 1, we have 4 ones, 2 zeros, 1, etc., etc., etc. Okay? So, essentially, we can now say that 3.95, alright, base 10 is equal to 11.1111, 0, 0, 1, etc., base 2. Okay? Now, the problem that we actually face, all right, is how are we actually going to represent this number? Notice that if I shift all of these numbers, all right, so essentially I can take this number here as 11.11110001, all right, that multiplied by 2 to the power of 0, that is equal to 0.1111, 4, 0, 0, 1, all right, times 2 to the 2. Would you agree that with me that these two values here are exactly the same? Essentially what I've done here is I've moved the points 2 times this way, therefore I had to multiply by 2 to the power of 2. Yes?
Yes.
Okay. So what we can now do is we can now represent the binary number that we have. So we know that the number that we wanted to represent all right, is negative. So minus 3.95 is negative. Therefore, sine bit is going to be equal to 1. All right. Our bias, our exponent is going to be equal to 2. All right. But we need to introduce the bias. All right. So we want so our biased exponent is going to be equal to 2 plus 4. Remember that this here is our bias. Okay, therefore that's giving us the value of 6. All right, and 6 is represented as 110 base 2. Okay, and we have this part of the mantissa. Remember that we can only represent 4 bits in this representation. Therefore, that is the remainder of our mantissa. Okay, so essentially, our binary number is going to be equal to 1. All right, for our sine bit, 110 for our biased exponent, followed by 1111 for our mantissa. Okay, so sine bit. This is our biased exponent. All right, and this here is our mantissa. Questions so far? Notice that if I actually had to convert this back, it's actually not representing minus 9.5. It's actually representing minus 3.75. Minus 3.75 exactly. Because I'm only using 4 bits in order to represent my mantissa. All right? Is this clear?
Sir, do you mind if you explain how you got the exponent too?
Mano.
Because
Mano, would you agree with me that 1 represents 3?
Yes.
Would you also agree with me that 0.95 is 0.1111?
Yes.
So essentially, I get this number. Mm-hmm. But this number can also be represented as that same number multiplied by 2 to the power of 0. Y was 2 to the power of 0. That is equal to 1. And anything multiplied by 1 is itself, correct? But, yes.
It remains the same.
It remains the same, yes. What I did then was I played around with this value over here. All right, so instead of having that being equal to 0, I made it equal to 2. Why? So that I can move this point 2 places that way. All right, therefore getting me this 0 point representation. All right, because we said that our mantissa, all right, over here, all right, we are assuming that this here is 0.1111.
Okay.
All right. That's essentially what I did. So that that is my exponent. That is where my 2 came from. All right. But in order to have it as a biased exponent, I would then need to add the bias. So 2 plus 4 is 4 is my bias, so therefore that will give me a value of 6. So this is the bias exponent that I need to represent.
Okay, that part okay.
All right?
Thanks a lot. Thanks a lot.
Any other questions, guys?
So we have a break.
Okay.
You want to go home?
Over here we have another example, all right, whereby you are asked to convert the number 0.09375 to a floating point number, as described before, all right, and you are asked to also find the error. So essentially, you would use the multiplication version, all right, in order to achieve this value, all right. So 0.09375 will be equal to 0.0011 if you actually had to calculate it. Okay, multiplied by 2 to the 0. All right. Essentially, notice that what happens here is because we are using this notation. All right, we are using the 0.00 or the 0 point notation rather 0.44 bits, and this is actually taking up 5 bits in order to represent it. Okay, it's going to end up with a situation whereby, all right, I'm going to miss out on my final bit if I keep it like this, in this case with the exponent being equal to 0. All right, so having my exponent being 2 to the power of 0, 0 plus 4, including the bias, meaning that means that we have a bias of 4. Therefore, my representation, if I did absolutely nothing and I worked exactly in the same methodology that I used before, essentially the binary number that I would be able to represent would be this over here. However, this number over here is actually representing the value of 0.0625, which is basically, all right, a substantial error. All right, it is basically a third off from where I actually wanted it to be. All right, how can we fix this? Well, if we play around with the exponent value, okay, we can actually get a much better result. So let's see this in action, all right? If we take this number, all right, so 0.00011, all right, multiplied it by 2 to the power of 0, you would agree with me that that is a valid number. However, I can also represent this same number as being equal to 0.11, all right? Multiplied by 2 to the power, how many times did I actually have to move the decimal point in this case? I had to move it by 3 times, multiplied by 2 to the power of minus 3. These two values are equivalent, all right? So notice now, with this representation over here, okay, I can come up with a floating point representation for that number, which is more accurate. Moreover, it's not just more accurate; it is exact. All right. In fact, if I try to calculate my new exponent, all right, my the exponent that I'm trying to represent is minus 3. My biased exponent is minus 3 plus 4. Therefore, it's giving me a value or a biased exponent of 1. Okay? And my mantissa now is 0.1100 base 2. Therefore, the 8-bit number that I'm representing, all right, is 0 for my sign bit, all right. 1 that we want to represent over here in 3 bits is 001, all right, and my mantissa is 1100. Okay, so again, remember, this is our sign bit, this is our biased exponent, And this one here is our mantissa. All right, and like this we have no error. So as you can see, the way that we can actually represent certain numbers can actually vary. All right, the accuracy and obviously the error that we're going to have when representing said numbers. In fact, whenever we use the 0 point notation, so if we're assuming that our mantissa is always going to start as 0 point, etc. All right? Essentially, we have an infinite number of ways that we can actually represent this number, really and truly. All right? Which is a bit of a problem, because what we want is that whenever we are representing a number, there will only be one correct way of representing that number. And that's where normalization comes into play. Okay? So, what is normalization? So, normalization is a methodology that is used within floating point representation, where you would avoid these leading zeros, essentially. Okay? These leading zeros over here would be avoided. So essentially, you would try to get rid of that. Not only that, with the mantissa, what we could also do is we could cheat a bit and assume that our mantissa, whenever we write our mantissa, instead of representing it as 0 point something, all right, we can represent it as 1 point something, all right, because all binary numbers are going to have a 1 somewhere, okay, except when you're representing 0. That's the only exception in the representation of all floating point numbers, essentially, all right. So essentially what you would try to do is you would try to represent your number as 1 point something, all right, times 2 to the power of your exponent. The reason why you're going to go for this 1 point something, all right, is there is only one representation for every single floating point number in this particular format. Does this make sense? This process here is known as normalization. So we're getting rid of the leading zeros, all right, in order to allow us to improve our accuracy with our floating point number. Any questions? In general, all right, what we would do is we would keep exactly the same exact format. We'll assume our mantissa starts with a 1 point something, all right? So our range is 1 point for this 8-bit system would be 1.0000 or 1.1111, all right? Thus giving us an extra bit, if you will, of precision, okay? Because it's assumed that it's there, all right? So it's not, we're not actually representing it. We are agreeing that that 1 point should be there, okay? Therefore, if we want to convert a number such as minus 0.07, we first and foremost would need to convert it into binary. So we'll take, so minus 0.07 is negative. So is negative, therefore sign bit is going to be equal to 1. All right? 0.07. all right, if you had to convert it into binary, all right, 0.07 multiplied, whoops, 0.07 multiplied by 2. So multiply that by 2 is equal to 0.14 multiplied by 2 again will give us 0.28. Actually, sorry, this should be 1,4. And this should be 0.28. Multiply that by 2 again. That is 0.28. Multiplied by 2 is 0.56. Multiplied by 2 again, 0.12. 0.56 multiplied by 2 is equal to 1.12. And again, you start over. All right, so 0.12 multiplied by 2 is 0.24. If you keep on going, you would see that 0.07 is approximately equal to 0.000 1000, etc. All right. So now, what we are going to do is we are going to normalize this number. So 0.000100011, etc. All right, is going to be normalized.
1.0001.
All right, if we normalize it, what we're going to try to do is we're going to try to take this point from here to behind the first bit, which has a 1. So we want to jump 1, 2, 3, 4 bits. So that would become 1.0001, like so, etc. Multiplied by 2, the number of jumps that we actually had. In this case, we want to try to make this number smaller, so minus 4 jumps, so minus 4. Okay? So essentially, what we're trying to represent is this number. All right, so we have our sign bit, which is 1. Our exponent, all right, which is minus 4. We need to add, all right, the bias. So we remember our bias is 4. So our exponent, okay, or biased exponent,
0.
is minus 4 plus 4, which is going to be equal to 0, which, if converted, will be 0, 0, 0 base 2. So our biased exponent will be 0, 0, 0. All right, and we're going to try to represent this number of our Mantissa. All right, so we're assuming that over here we have our 1 point. So we'll write 0, 0, 0, 1 for our Mantissa. Remember that we have an assumed 1 point over here. All right, and that would be our sign. This will be our biased exponent. And this will be our normalized Mantissa.
Sorry for all the noise.
Are there any questions, guys?
Better now, thank you.
Okay. Over here we have yet other examples. I would suggest that you go over them again at home in order to see whether or not you have understood this implementation, and if so, again, do not hesitate to contact me. All right. Now, essentially, whenever we're talking about floating point numbers, computers rarely work with 8-bit numbers because 8-bit numbers, as you can probably imagine, are very restrictive in terms of their range. In fact, if we take a look at our biggest magnitude that we can actually represent, where we have our bias exponents being all 1 and our mantissas being all 1, that will allow us to get a value of 15.5. All right. On the other hand, the smallest value that we can represent, where all of our bits are 0 except our assumed, all right, hidden bit, then essentially our smallest number that we can represent, right, or the smallest magnitude that we can represent is 0.0256. So we although we do have more range and again more accuracy, 8-bit might not actually be enough in order to represent the majority of the numbers that we're probably going to be facing. All right? And that's where certain standards have been implemented. One particular standard of a floating point representation is the IEEE 754 floating point standard. All right? There are two forms of the standard, which is the 32-bit number and the 64-bit number, just for your information for those of you who are doing Java this year. You know, when you talk about the float, remember we said that it's a 32-bit number. Essentially, it's using this number, right? And remember the double, right? Why is it called a double? Well, it's using double the amount of precision. All right. We are required in this course, in order to understand, all right, the IEEE 754 standard for the 32-bit number. All right. Now the 32-bit number is split up accordingly. So you have 1 bit again, which is used for the sign bit. All right. 8 bits for the biased exponent, and the remainder 23 bits are the mantissa, which is assumed to be normalized. Okay. So essentially, if we have to look at it diagrammatically, that's the word that I wanted to say. All right, the first bit that represents the sign of our number. All right, the next 8 green bits. All right, specify the exponent that is actually being stored. Remember that in this case, for the IEEE 754 standard, the bias is always 1 to 7. Okay, it's important that it's 1 to 7. All right, because it's part of the standard, and the remaining 23 bits is basically the mantissa with an assumed 1 point over here. So it essentially is a normalized mantissa, kind of like what we did over here. All right. Now, you're going to be asking me, should you be able to convert to this particular representation? Yes, you should be able to. Essentially, the only difference is that instead of working with 8 bits like you have over here, you'd be working with 32 bits. So the exponent values might be a little bit larger. All right, and and you'll have more bits in order to represent your binary number. For an exam situation, please keep in mind that we obviously know that you only have 2 hours in order to answer a question. All right, so we're not going to be giving you a question whereby you'll have to fill all of these bits over here, unless it's very easy in order to see the pattern. All right, so keep in mind that we should know what we're doing, at least as lecturers. Okay. Are there any questions?
None from my end, thank you.
Because I already saw some people maybe saying, "Oh, 32 bits, right?" So that's understandable. Okay. one thing that I would also like to point out is that whenever we're working with the IEEE 754 representation, all right, there are a number